Little Jay is an aspiring musician and a piano prodigy. He's studying to compete in a prestigious competition at the year's end. He's struggling to master one of the more complicated pieces in his repertoire. Luckily, a research team out of Georgia Tech is pushing the boundaries of what's possible with ubiquitous computing to deliver Jay the tools he needs to succeed. Over the past several years, our mentors, Caitlin Syme, Celeste Mason, and Thad Starner, have done research into an area called passive haptic learning, which allows users to have their muscle memory trained through vibrating wearable devices. This research has many potential applications. For example, in the medical world, it could help partially paralyzed stroke patients regain some degree of motion in their hands, or to teach blind people Braille. Some of the most promising results so far have been in the area of teaching piano and other musical instruments. Through vibrations on a wearable glove, students are automatically trained in piano melodies without having to be at a piano or even paying attention. The purpose of our project is to build an end-to-end pipeline that allows a young music student like Jay to go from a frustrating musical score all the way to ideally sized musical lessons vibrating in his fingers, teaching him music through the power of passive haptic learning.
We are building a software system to generate lessons for the gloves from music. To do this, we have a multi-phase lesson generation workflow. First, users obtain a MIDI file for a given song from an online repository. There are many repositories of both creator and community-made MIDI files, including MuseScore, freemidi.org, and oftentimes Google Drive links and YouTube descriptions. Once a user has gotten the MIDI file for a given song, finger patterns for the song must be assigned to each note. MIDI files do not contain finger patterns, they only contain the note for a given time and the velocity of the note. To assign fingerings, we use a cost algorithm to assign fingerings for each note.
So first technical issue is fingerings. And the main issue with fingerings is the data formats that we deal with when handling music. So the first data format is MIDI, and MIDI isn't optimal for our usage because it doesn't have fingering data for each of its notes. And music XML is another data format that we use, but it's also not optimal because the music files that it comes with doesn't have fingering data for each and every single one of its notes. It only has fingering data for certain crucial notes, which isn't conducive for our solution. So the way we fix that is by utilizing an open source Python library called Piano Player. Piano Player essentially takes a variety of features, such as the size of a player's hand, the number of measures that you want to convert, and the distance between each of the fingers in one hand, and the time that each note is played, in order to generate a comprehensive fingering for each and every note in the piece. And why it's good because it incorporates a lot more features into its algorithm than previous solutions, and that gives it a higher accuracy. And also because it's not based on a static lookup list of different fingerings, of different probable or improbable fingerings, and instead it's a dynamic algorithm that evaluates fingerings in real time, and in doing that it's more accurate. However, while analyzing this solution, we found a bunch of issues with Piano Player's source code that contributed to certain insights that we saw. So the first issue was that while converting different phrases of music into their corresponding fingerings, the main issue was that certain fingerings were different for the same phrases of music. So that caused a consistency issue because you would have the same phrase of music in different parts of the piece, but they would have different fingerings even though they had the same notes played on them. Even though intuitively I wouldn't do that myself. So that made it hard in terms of maintaining consistency. Second, it doesn't account for hand jumps or jumps where I have to play notes on one end of the keyboard and then move on to another end of the keyboard within a very short time frame. And that makes it problematic because it assumes that I'm playing that with one hand without moving anything. So the fingerings don't account for that, and it makes it harder for a player to accurately play that note. Furthermore, it also doesn't account for multiple streams of music. So what this essentially means is that in certain varieties of music, such as Baroque music or Bach's music, certain clefs have notes that are not connected together but placed in separately. like a choir almost, different voices in a choir. So that translates over into a piano piece. And the issue with that is that the fingering algorithm doesn't recognize the lower voices and only recognizes the higher voices. And that makes it difficult because certain notes go unfingered, and that might make it harder for the end user to use it properly. So we have two solutions that we thought about on how to fix this. The first solution that we have is we can comprehensively analyze the source code and analyze what each segment of code is doing, and then potentially rewrite certain segments of code. In that, it'll help us fine-tune the fingering algorithm to make it a lot more useful. And if that doesn't work out for us, we can also utilize solution 2, which is to utilize additional hardware components such as the inertial motion sensor, for example, in order to capture more data about a music piece, so that we can actually create more effective fingerings for our end user.
This process outputs a music XML file, which we use as an intermediary because it stores fingering data. Music XML is also a common file format that can be used in external sheet music editors, so users can tweak the generated fingerings to fit themselves better. With a music XML file, we can then encode it into lesson files. And then with the lesson files, we can play them back on the gloves.
So once the song has been converted into a music XML format and had fingerings assigned, the next step is to convert the score into a format that is easily readable by the embedded microcontroller on the glove, and also to break up the song into bite-sized chunks that are ideal for learning. So previous research on passive haptic learning has revealed certain conditions under which this method of learning works best. For example, it works best on rapid sections of songs or sections that are repeated throughout the song. Also, the ideal number of stimuli is about 12 to 17 notes. So our plan is to build software that will start with these parameters and then add in computational musicology. So we'll look at things like when chords or cadences or musical motifs start and end in the piece. And by connecting the cognitive research with the musical theory, we will be able to break up the score into easily digestible and musically coherent pieces that are ideal for this method of learning. And once the song has been broken into these chunks, we've written a Python script that will parse through the score and take into account all of the notes, which type of notes are being played, which finger and hand is playing them, as well as things like the limitations of the hardware and other conditions that work best for passive haptic learning, and output a text file which details when each motor should vibrate and for how long each motor should vibrate. And once we have these text files representing each of the lessons, each part of the score as a lesson, it's time to send them over to our gloves.
Over the next couple of weeks, it is our job to combine all these components together to create one cohesive pipeline, from uploading a MIDI file to generating the fingerings to actually working on a prototype device. We have all the components to build a prototype device, like this Arduino Mega, and within the next week or two, we will be building prototype gloves to actually evaluate our software. We have a lot to do, but we've also done a lot as well, and we are very excited to see where this project is going. For the prototype specifically, by the end of the semester, it is our goal to have a website where you can upload a MIDI file, and then download the lesson file to play back on our prototype gloves using the Arduino or the Cduino. This is our current website. It shows a list of lessons, and for lessons that have not been generated, allows you to upload a MIDI file. And it will let you download the lesson for ones that have been generated. The web frontend talks to our backend API, written in Python, and hosted on Google Cloud Platform. Our next step is to hook up our backend API up to the fingering generation and lesson generation modules for the complete generation flow.
Thanks to passive haptic learning, I can now play this.